Consider now this problem. Here we have a transmission line of a given line length, 0.134 lambda, and instead of knowing the load impedance, as we did in the earlier examples, in this case we know the input impedance. The load impedance is, in fact, what we want to determine, what we seek for this particular problem. We know, for some reason, the input normalized impedance. We seek the load normalized impedance. Well, we can use the Smith chart to solve this problem, and really it's the same as the earlier problems we solved, only sort of in the opposite direction. There are 3 steps to solving this problem, but for this example, the first step is converting not the load impedance to the load reflection coefficient, but in fact converting the known normalized input impedance to the input reflection coefficient. And to do that, we simply locate the value on the Smith chart where the circle of constant resistance, R equal to 1, intersects the circle of constant reactance of 1.4. In other words, the impedance that corresponds to the known input impedance, normalized input impedance for this problem. We observe our Smith chart and we find the contour for constant resistance of 1, the R equal to 1 circle, is this blue circle, and we can determine that by looking closely at the numeric index as this circle crosses the horizontal axis, the real axis of the complex gamma plane, and we see that circle corresponds to a value of R equal to 1. For the reactive part, we're looking for the contour of constant reactance, x is equal to 1.4. We go up and we see where these constant reactance contours cross the unit circle, and we find the value of 1.4. And we know it's 1.4 positive, not because it says 1.4, but because this value is in the upper half of the complex gamma plane. It is in the inductive region. And so we've identified 2 contours, the R equal to 1 contour, the X equal to 1.4 contour. And of course, at the intersection of those 2 contours is a point. The point that's not equal to the impedance of the, or the normalized impedance, input impedance. It is the value, the location of the input reflection coefficient of that input impedance on the complex gamma plane. So we put a marker there on our Smith chart, the location at the intersection of these 2 contours. And again, we know that that location is the proper location on the complex gamma plane for gamma in, the value of the reflection coefficient that has been transformed from our known input impedance in the normalized impedance plane onto the complex gamma plane, in other words, onto the Smith chart. Step 2 then is to parametrically plot the reflection coefficient function along our transmission line. In the earlier examples, we plotted this function from the load reflection coefficient back up the line to the input reflection coefficient. But in this problem, we know the input reflection coefficient. We're trying to determine the load reflection coefficient and ultimately the normalized load impedance. So in this case, we're going to parametrically plot the reflection coefficient function from the input reflection back down the transmission line rather to the load reflection coefficient. In this case, then, we're moving up the transmission line, or down the transmission line, rather, I should say, down the transmission line to the load. The index, the position index Z, is increasing, and because the position index Z is increasing, the value of 2 beta Z is increasing, we have a situation where our angle of reflection coefficient is increasing. We are rotating around the complex gamma plane in the counterclockwise direction. In other words, we're rotating around the Smith chart in the counterclockwise direction. That's the only difference between the earlier examples. Instead of striking a circular arc now that rotates in the clockwise position or clockwise direction as we move from the load back up the transmission line to the input, now we're going to plot strike a circular arc which rotates in the counterclockwise position as we move down the transmission line toward the load. So what we're doing is evaluating our reflection coefficient function at the beginning of the transmission line. That's the value of gamma in. And then we're moving down the transmission line a distance of 0.134 lambda to the end of the line where the load is located. Again, a parametric plot of the reflection coefficient function on the complex gamma plane. So again, as we're moving down the transmission line toward the load, the position index z is increasing, which means the phase value of the reflection coefficient, 2 beta z, is increasing, which means we are rotating counterclockwise around the complex gamma plane, which means we're rotating counterclockwise around the Smith chart. And of course, we rotate around the Smith chart over an arc angle, which is commensurate to the value of 2 beta L, where the L is the length of our transmission line, in this example, 0.134 lambda. We can do the calculation and find that that value is equal to 0.36 pi radians, or 96.5 degrees, the angle counterclockwise of the rotation. So we go back to our Smith chart, and again we've identified the proper location on the Smith chart for gamma in. It is at the intersection of the r equal to 1 contour, the contour of constant resistance of 1, and the x equal to 1.4 contour, the contour where every point corresponds to a impedance whose reactance is plus 1.4. We put our pencil there, and then we draw a straight line from the center of the Smith chart, the center of the complex gamma plane, outward through the point gamma in, outward to the outer scale. Now in this case, we're going to use a different outer scale than we've used previously. In this situation, of course, we're moving from the input down the transmission line to the load, and so we're moving toward the load. And so because of that, we're going to use the wavelengths toward load scale. That is the electrical index that increases as we rotate counterclockwise around the Smith chart, which is of course the direction that we'll be rotating. So if we use this scale, our index is going to increase as we move in the counterclockwise direction, and it is a little bit easier to use than the other scale because we don't have to do subtraction. Specifically, if we follow this line out to the edge, we see the value for the wavelengths toward load scale, this electrical index that we have for a transmission line, is about 0.326 lambda. Again, that number has no significance to us at all. But we take that number and we add to it the electrical length of our transmission line, 0.134 lambda. We add 0.134 to a value of 0.326, and we get a value of 0.460. So we're going to move along this outer scale, looking at, again, wavelengths toward the load, until we get to a value here of 0.460. And then we're going to put a mark at that location. We're going to take our straight edge, and we're going to draw a line from the center now outward to that mark. This gives us the boundary where we need to stop when we parametrically plot our reflection coefficient function, when we use our compass to strike a circular arc around the complex gamma plane. So we take the compass and we put the pointy end here and the pencil here, and we strike a circular arc. Okay, this isn't exactly circular, but it's a close proximity to a circular arc. We're parametrically plotting the reflection coefficient function. Again, that's always important to understand. That's what we're doing. Parametrically plotting it as we move from the input of the transmission line down the transmission line to the load. And we rotate around until we meet this boundary. We meet this mile marker of 0.46. Again, 0.46 doesn't have any significance other than that's means that we've moved our requisite distance of 0.134 lambda. So we stop at that point. And when we stop there, we know we are on the proper location in the complex gamma plane for the true value of gamma L. If we were to measure the distance from the center to that point, that would give us the magnitude. If we were to look at the rotation angle around for that point, that would be the reflection coefficient angle for gamma L. Again, generally speaking, we don't determine those values because we don't explicitly care what the value of gamma L is. What we seek to find is instead the value of the load impedance, the normalized load impedance. And that step is our third of our three steps. So the third step is to transform this load reflection coefficient to the load input impedance, so the normalized load input impedance. And instead of going through and using this equation, which we could do, we can more quickly determine the answer by simply looking at the point for gamma L and seeing where the contours of constant resistance and constant reactance intersect with that point. If we look closely, we see this blue circle, which is the contour of constant resistance of 0.29 intersects that point. And likewise, this contour of constant reactance intersects that point. And if we look up here and look at our scale and carefully evaluate it, we find that that contour is for a reactance of 0.24 plus 2.4 because it is in the inductive region of the complex gamma plane. The upper half, the value is positive. So we've gone through and used our Smith chart to start with an input impedance of 1 plus j 1.4 on a transmission line of 0.134 lambda, and we're able to determine the load impedance at the other end of the line for that situation. And notice we never had to pick up our calculator or do any sort of complex arithmetic or mathematics.